Okay, yes, I can start. So good morning, everyone. I'm Vasileiou. I'm a PhD student at RWTH University of Aachen under the supervision of Professor Christopher Morris. And in this presentation, together with Thien, we'll try to walk you through the main ideas and contributions and challenges in the area of generalization theory for graph learning. So here is the outline. First, I will very briefly go over some very basic stuff we have seen many times these last 2 days. Then I will try to formally define what is the generalization theory and what is the goal in generalization. And then I actually will make the distinction between two parts of this talk, the in-distribution generalization and the out-of-distribution, while I will take care of the first part of the in-distribution results, while Thien later we will go over the results on the out-of-distribution generalization. So yes, as we have seen, graph data appears everywhere. We can model molecules as graph data, citation networks, social networks, and based on the kind of label we want to predict, we can distinguish between graph level, node level, and edge level tasks. We have seen this many times the last 2 days. And what is graph representation? The first idea in graph representation is that for each graph, we want to compute a vectorial representation on some vector space, encoding as much structural information as possible of the graph, and then apply any machine learning algorithm on this vector space. So the most known architectures we have seen for computing these vectorial representations are the message passing and graph transformers, where a basic difference on these two architectures is that in the MPNNs, we update the node features in a local fashion, so each node gets information from neighboring nodes, while in transformers, in graph transformers, each node updates its current node feature, taking some information from all nodes in the graph with some proper weighting. And then we have the readout layer when we are in the graph level tasks. Okay, let's now introduce some necessary notation for defining the generalization. First, we have our training data, denoted by this calligraphic S here, consisting of IID sample of labeled graphs. So there are graphs with some labels. In this case, are molecules with the toxic or not toxic label. And they are IID sample from some underlying distribution mu. Then we have the learning process when we train our model by minimizing the empirical error, which is just the average error of our training set. And the minimization is taken over a hypothesis class. So for now, you can think of this hypothesis class as a family of MPNNs. So we minimize, and that means that the predictor, actually the function we compute, depends on the training set. And then what the main task is to make some predictions for some new unseen graphs some new examples that we observe. And here is exactly one where we make the distinction between in and out of distribution. So we can assume that this new graph that we have to predict its label has come from the same distribution mu as our training set, or from some completely different distribution mu prime, where we say that we are in the out of distribution setting. So for example, you can think that we train our model on very small molecules, and we want to make some prediction on some large molecules. In that setting, it would make sense to assume that we are in the out of distribution setting. For now, forget about the out of distribution. Then we will go over the main ideas in this area. There's slightly different, and say that this graph G has been sampled from the same distribution. Then we can define the expected loss as the expectation of our loss, where now the expectation is taken over this underlying distribution, like our training set. So what is the main question that the generalization theory aims to answer is the following. So to what extent can we trust that the model performing well on the training set will also perform well on some unseen graph? Or slightly more formally, the question can be stated as follows. Is the empirical error, which is the average error on the training set, a good estimator of the expected error? And to measure how good this estimator is, we will bound this difference between the empirical and the expected error And of course, we are interested in probabilistic bounds because there is also some randomness over the training set we have sampled. So we are interested in bounds of the following form. With some large probability, we aim to bound the difference between the empirical and the expected error from some term that will probably depend on the structure of the hypothesis class, on the loss function we assume, and of course on the training set. Okay, we are in the in-distribution setting. Let's have a second look at the difference we want to bound. For simplicity, we say that we are in the binary classification setting and we use the 0-1 loss. So each term of the sum here can either be 0 or 1. And if we look at this difference here is just a difference between an average of random variables and their expectation. And the first thing that comes to our mind is to use any concentration inequality. For example, the most simple one being the Chernoff bound. So for the Chernoff bound, we have two equivalent formulations. We just need an IID sample of n random variables, and then we can bound the difference between the average sum and their expectation. But things are not too easy here because there is a reason we cannot apply this Chernoff bound directly to this difference, and the reason is that this term here is not an IID sum. And why is not an IID sum? Because even though we have assumed that the samples have been sampled in an IID way, our classifier depends on the training set. So we have trained our model based on a fixed training set. So all these terms of the sum depend on the training set we have used to train our model. So to overcome this, we say that we aim to bound the supremum of this difference. And this is why we call this kind of bounds uniform generalization bounds. So if we now bound the supremum, each term here is an IID sum, but this comes with a cost that we now have to bound something much larger, since we have to account for the worst case behavior in the hypothesis class. So let's say that we are in this very simple toy example where the hypothesis class consists of a finitely many function. That's not very realistic, but let's see what we would do in this case. And we aim to bound this difference, the probability that this supremum is larger than some number epsilon. And of course, the probability of the supremum can be written as the probability of the union. At least one of this difference should be larger than epsilon. And this is bounded by the sum of the probabilities. And we apply the union bound, the Chernoff bound, at each term of the sum, leading to the following first generalization bound for this very simplistic setting, right? So this generalization bound says that the difference, the supremum over the hypothesis class for the generalization gap can be bounded by this term here. And of course, the larger the generalization bound, the larger the upper bound is, the worse the generalization performance of the model. And this means that the richer our hypothesis class is, the worse the generalization performance that it will have, and induces some trade-off between the expressivity and generalization of the hypothesis class. Okay, so far this is a very simple setting, but that's not actually the case because we train over parameters that live on some vector space, and in practice the hypothesis class consists of infinitely many functions. So for that we need somehow to observe the following, so that given that we are in the binary classification setting, for any finite set of graphs of some size m, the number of possible labelings that a function of a hypothesis class can actually realize on this set is at most 2 to the power of m. So what actually matters is not the cardinality of the functions in the hypothesis class, but how many labels can our hypothesis class realize. And based on this, we define the VC dimension. That is a concept for measuring the capacity of the hypothesis class in that sense, as the largest integer m, such that the hypothesis class can realize all 2 to the power of m labelings of this dataset. So for people that are not very familiar with the VC dimension, I think the following example is very intuitive. So let's say that we are in the space of two-dimensional real vectors, and our hypothesis class are just linear separators. And we can see that if we are given any possible dataset consisting of 3 points, then no matter what are the labelings, we can always find a line separating the dataset between two classes. And if we are given 4 data points here with this specific label, we cannot find a line that would separate the classes, which implies that the VC dimension is exactly 3 in this very simple setting. So why do we care about the VC dimension? Because based on the VC dimension, we can derive some generalization bounds from this very first theorem in 1964 by Vapnik and Chervonkakis, where we can see now that the cardinality of the hypothesis class from the toy example has been lifted to the VC dimension plus some logarithmic term of the hypothesis class. So far, the idea of the VC dimension seems to be somehow related with the distinguishability power of the hypothesis class. And this is what exactly Christopher and Floris observed, and with other people, they proved that if we are in the space of graphs with at most n nodes, and this D indicates the number of the dimension of the initial node features, and the hypothesis class consists of the MPNNs with some aggregation, and for the activation function, you can think of any Lipschitz function for this setting. They prove that the VC dimension of this hypothesis class is exactly equal to the number of 1WL equivalence classes induced on this space of n-order graphs. So what is this MNDL? Is exactly the number of equivalence classes induced in the space of graph under the 1WL equivalence relation after L iterations. So yeah, that was the first bound on the graph level task using the VC dimension for MPNNs. And what they actually use in the proof is the expressivity limitation of MPNNs in terms of the 1WL algorithm. But what are the issues with the VC dimension that makes us to move to different generalization bounds? So first of all, we don't know that the VC dimension is always finite. In this case, we had to assume that we have to restrict ourselves to the settings of n-order graphs. And another issue is that the VC dimension is a purely combinatorial tool that completely ignores the structure of the MPNN. So for that, we define the... Yeah.
So n is what?
Small n?
Yeah.
It's the maximum number of nodes on the graph.
Okay.
So there are n-order graphs.
And d?
D is the dimension of the initial node features.
Is an L? No.
Yeah, L is the number of layers of the MPNN and also the iterations of the 1WL algorithm.
Okay.
Yeah.
How does the right-hand side depend on D? Does it depend on D?
The right-hand side?
Yeah.
Yeah, that's a very good question. So this MNDL, we don't exactly know how does it scale with n. A very known result is that for very large n, almost all graphs with probability 1 are 1WL distinguishable, which means that for very large n, this scales exponentially with probability 1.
I was more interested in the dependence on D. So if
on D.
What dimensions, how does this affect the number of equivalence classes?
How does MNDL scales with D, you mean?
Does it depend on D at all?
Yeah,
it depends in the sense.
If then you prove the equivalence, you say that basically what Vasileiou does is like a hashing, and you have to be able to implement that hashing with your MLP. And if the MLP is very low dimensional, you may not be able to approximate that function well.
Okay.
But the exact dependence, I don't know, I'm not sure.
Yeah.
So I mean, you can view it as the initial colors of 1WL encoded as Boolean features.
Yeah.
And then you just get some multiplicative term from let's say, uniformly labeled graphs.
So D measures the availability of colors you can use for the initial coloring in a graph.
Yeah.
So yeah, it has to depend on D.
That makes sense. Yeah.
Okay, sorry, it's just too fast.
Yeah.
This ignores, it's a purely combinatorial, can you just ignore, any VC bound is a purely combinatorial tool. And what is this comment? It ignores the MPN and architecture.
That comes to the Rademacher complexity
and
structure.
it's only some aggregation, especially the lower bound. The lower bound, so this is an upper and a lower bound.
Okay.
And the lower bound requires some aggregation.
Okay.
And it's like MPNN of all sizes or something like that? Like how many features, what depth?
So the
The
upper
depth is
bound
L.
holds for
Oh,
anything.
Yeah,
But for
but
the lower bound, you have
has to
a
be
certain.
sufficiently large to.
So the dimension will depend on n,
Yeah.
the order.
So this is
Okay. Yeah.
So the proof doesn't depend on the loss you're using in your GNN?
Sorry, I couldn't hear you. If the proof depends
Does the proof account for the loss you're using in your GNN?
for which? Sorry,
The loss.
for the loss. Yeah, we are considering the 0-1 loss and the binary classification setting. Okay. So let's now define the Rademacher empirical complexity as follows. So these sigmas are Rademacher random variables taking the values 1 or -1 with probability 0.5. I will go through the definition in a few moments. So this is a different capacity measure for penalizing the capacity of the hypothesis class. And what actually measures, it's and depends of course on the hypothesis class, but this time, in contrast to the VC dimension, it also depends on the data set. So you can see that this is always finite because in the binary classification setting, every term here is bounded by 1. So yeah, the empirical Rademacher complexity measures how well can our hypothesis class fit random noise. And to see that, first, you just should see this sigma I as the actual label. Let's say that this sigma I was the actual label, forgot about the expectation. Then this sum increases while the prediction and the actual label agrees and decreases if they disagree. So if we take these actual labels to be just the random noise, then the Rademacher complexity measures how well can the hypothesis class fit this random noise. And we have the
What is S? Depends on H and S. What is S?
sigmas. This sigma is
That in the first bullet item depends on H.
S is the data set. Yeah. So it's a finite sum. And Mori et al. Derived this first generalization bounds using a slightly different loss function, an extension of the 0-1 loss. I'm not going to get into detail for that, but it's just a simple extension of the 0-1 loss. And they prove that, again, uniformly, the generalization gap can be bounded by the Rademacher complexity and this term here, which is very similar to the confidence term we had in the VC dimension. So what is important is that
Sorry, what is H gamma? Is that an H gamma?
okay, yeah, that's okay, my omission. So H is the hypothesis class of MPNNs, and H gamma is the composition of MPNNs with a loss function. So it's a new hypothesis class. Okay?
So it's the MPNN hypothesis class composed with the loss.
On fixed size data sets?
It's a no, it's a function class.
So Rademacher complexity of that class, right?
Yeah.
Yeah, and Rademacher complexity typically will like shrink with the number of like data points. It will shrink maybe like 1/squared n or something like that, ideally, or like complexity divided by squared n.
Mm-hmm.
Is like this.
That's good. Yeah. Okay. So then, yeah, the goal for deriving a valid bound would be to bound the Rademacher complexity of this hypothesis class. And the first result on this was proven by Vikas Garg and Stephanie in 2020. And just a disclaimer: the following proof, the following slide, it's not a proof or a sketch of proof. It just gives some insights of how does the proof for bounding the Rademacher complexity of for MPNNs differs from different neural network architectures. So we want to bound the complexity of the hypothesis class, and to do that, let's say we want to bound the complexity of the model, looking at the computational graphs on the model. For example, if we were interested for MLPs, we know that the MLPs can be completely described in a very informal way, right? From these computational graphs. So we can see that the complexity of the MLPs somehow depends on the complexity of these graphs. So increasing the complexity of these graphs by adding more layers or increasing the width of the hidden dimension leads to larger empirical Rademacher complexity, and therefore to larger Rademacher upper bounds. We can also see the recurrent neural networks as computational graphs with this chain can be illustrated by this chain here. And again, we can see that this structure is much more simpler, and RNNs usually have a lower Rademacher complexity than MLPs. So what is different in MPNNs is that the computational graph is not fixed, but it actually depends on the structure of the actual graph, of the initial graph. Since for computing the node vector for each node in the graph, we have a computational tree. So this tree actually corresponds to computing the node feature of node UI, and each node has as children the neighbors of the node in the initial graph. So for somehow illustrate the computational complexity of the MPNN, this would depend, of course, on the initial structure of the graph. And if we say that we use a readout, a mean readout layer, and then we can express the complexity of the model in this very informal way as the weighted average of the complexity of its tree that appears on the graph. So to bound the complexity of these models, we would bound the complexity of its individual tree. And how can we bound the complexity of its tree? By bounding, let's say, the allowed maximum node degree in the initial graph. For example, if we assume that the node degree here is bounded by some very small number, in the extreme case, for example, by 1 or 2, then all these computational trees will look like chains. And then we would expect that the bound would be somehow similar to this architecture of RNNs. And this is what the results actually show, the first result. So these are the assumptions. We are using MPNNs with some aggregation linear function and some Lipschitz. We replace the ReLU with any kind of Lipschitz function, activation function for each step. And then we assume that the maximum node degree is bounded by some capital Q, and we have a percolation constant, as we say, which is actually a function depending on these Lipschitz constants of the aggregation functions and the activation function we are using. So yeah, this is not very important. And the result shows that the Rademacher complexity actually scales, as you can see in this table, where node again is the node feature dimension. L is the number of layers, capital N is the sample size, and this gamma is the parameter that depends on the loss function. So we can see that increasing this Q, which is the maximum node degree we allow, also increases the bound. And what is very, very interesting in these results is to compare the following bounds with the bounds other people, Sen et al., proved for the RNN's case. And we can see that these bounds are very similar. They only differ on this term Q here. That's the only thing missing, which means that if we actually take this Q being equal to 1, what we previously said about the computational trees that are chains and would lead to the RNN computation is actually true under this setting. So that's a very first comparison between the generalization bounds for MPNNs and neural networks. So C is a constant that depends on the Lipschitz constant of the activations function we are using. So we say that instead of ReLU, we can use any possible Lipschitz function as an activation function. So it depends on the mechanisms for the aggregation at each level. Actually, it is the product of these Lipschitz constants. So these are the bounds we obtain from the Rademacher complexity, and these are the comparisons with the results from RNNs. But still, we are not done. There are still many issues, even for Rademacher complexity bounds. And the most important one is that we are still using a very impractical loss function. So the margin loss is not the loss that we are minimizing to train our network. And of course, all these bounds depend on on the magnitudes of the parameters and completely ignore the geometry of the space of graphs. So this leads us to define to define the covering number-based bounds, which have a very intuitive explanation to my mind. So you can think that we can start from this very known result by Morris and Su et al. And other people have rephrased this result. So we have this naive similarity property, knowing that if two graphs are, yeah?
So you said magnitude of the parameters. Do you mean like the hyperparameters or like the weight, I guess?
The dimension of the initial node features, the number of the hyperparameters of the model, yeah. So we have this naive similarity property stating that two graphs are 1WL equivalent, implying that they have the exact same MPNN outputs. And I call this a naive similarity because it is based on some naive pseudometric defined between graphs. So two graphs are either in distance 0 if they are 1WL equivalent, or in distance 1 if they are not. And exactly this property leads to the VC bounds, as we saw previously. And now the idea is to use a more fine-grained similarity property. So let's say that somehow we can find a distance between graphs, denoted as dg, having the following nice property. So if two graphs are close under this distance, then we can guarantee somehow that their MPNN outputs, these vectors on this vector space, are also close in the L2 norm, for example. Actually, this property mathematically is a Lipschitz property or a uniform continuity property with respect to this distance. And this fine-grained similarity property, I mean, we haven't talked about this distance metric yet, but this fine-grained similarity property is exactly what leads to the covering number-based bounds. And before I formally state what are the covering number-based bounds, I will give the definition of the covering number. So let's say that we have a space of graphs and the distance on this space. Then we call an epsilon cover of this space a subset of graphs, a subset of elements of this space, such that if we take the epsilon ball away from these elements, we will cover all the space with respect to that distance. So this is an epsilon cover, and then we can see the covering number as the epsilon cover with the minimum cardinality. So the covering number of a space of graphs with respect to some pseudometric and some radius epsilon is exactly the minimum, the cardinality of the minimum epsilon cover that can be constructed on that space. So based on this definition, we have the following theorem for the covering number generalization bounds in the very general form for the binary classification setting by Sweet-Manor. And this theorem can also be extended to the regression setting or to multi-class classification. But we keep things simple here, presenting the binary classification. So if we have a space of graphs with some proper pseudometric satisfying the following assumptions. So each function in the hypothesis class should be cell-Lipschitz. And what is important here is that this C should be the same for all functions in the hypothesis class. So this is a Lipschitz property for the hypothesis class. And the loss function should also be a Lipschitz function. For example, the cross entropy loss is such a function. Then we can derive the following generalization bounds for any possible function in the hypothesis class. So this is also a uniform bound. It bounds a supremum. And now the bound, actually, it's not a single bound, but it's a family of bounds, because since we can use every different radius to derive a different bound on the generalization gap. So the actual bound is the infimum over epsilon of the right-hand side. So in order to apply this theorem in the space of graphs, there are two things that we need to derive. We need to define a proper pseudometric on the space of graphs that would satisfy this very interesting property. And second, we need somehow to ensure that the covering number with respect to this metric is finite through some compactness argument or by assuming that our space of graphs is finite. So this is actually the two most common approaches for doing the second one. So I mean, these two problems are connected because the covering number depends on the pseudometric. So the first approach to show that this covering number can be bounded actually is the simple case is to assume that we are restricted to some finite space of graphs, for example, n-order graphs with at most n nodes. The second approach, I will try to illustrate the second approach in this commutative diagram. So to understand this diagram, we first need to think that MPNNs are actually functions from the space of graphs to the space of graphs, since they just take a graph and then they return the same graph with updated node features. So how does this compactness argument work? We have a random space of graphs. Then we should somehow carefully map this space of graphs to some compact space. For example, you have here about graphons and the cut metric yesterday and on Monday. So we should carefully map this each graph to a graphon, let's say the induced graphon. And what do I mean by carefully? Also, actually, we should also define an MPNN architecture on the space of graphons. And the choice of MPNN, of how do we define the MPNN and how do we map graphs to graphons should be very consistent, such that if we apply the MPNN on the initial graph, or if we apply the MPNN on the induced graphon, then we would take the exact same result. Actually, if we compute the MPNN and then we map to the compact space. And of course, we need to, again, to define properly a readout layer for both cases, such that the vector would be the same. So this ensures that the node representation should be aligned, and this that the graph vector representation are the same. So in two different works, in the first work by Ron Levy in 2023, this space was exactly the space of graphon with a cut metric. He proved compactness of that space, and then he defined somehow a message passing mechanism on the space of graphons. And he also derived a bound on the covering number of that space, a very loose bound, but it holds for the family of all possible graphs, no restriction on the number of nodes in the graph. In an alternative work, Rauch-Vergia and Stephanie and Ron again, they proved that this space could also be a space of iterated degree measures with some Prokhorov metric defined on this space. That's a different compact space. And they derive a similar construction. So let's see how these pseudometrics so if we want to define the pseudometric directly on graphs, so such that they satisfy this Lipschitz property, we need to go through some definition using the computational trees of nodes. So let's see what are some very common distances between graphs that satisfy this Lipschitz property for MPNNs. So we want to define a distance between these two graphs. First, and we have some fixed layer, some fixed depth 2, for example, in this case. So we first compute all computational trees for each node in both graphs, where these colors actually represent the initial colors in the graphs. Then we pad these trees with these gray nodes with a 0 node feature, such that both forests or all trees would have the same structure. And then we can see a distance between these two graphs as an optimal alignment problem between these two forests. So without being very formally, this can be seen as an optimal transport problem from the multiset of the computational trees, from this multiset to this multiset, or you can treat them as two different forests and measure the node level distances, the minimum node level distances under every possible edge preserving bijection. Actually, these two definitions have been proven to be equivalent, and the Prokhorov metering of the space of iterated degree measures works very similarly. Is everything clear for these distances? Okay. Let's now finally see an interesting connection between covering number bounds and the VC dimension bounds. So
What if you study different structures, for instance, instead of these unravelings, that come from the
MPNNs?
Huh?
Instead of MPNNs, I mean, you have to go through the unravelings because you are using MPNNs.
Yes, but if you were using higher order MPNNs, you would use these more complex structures somehow, right? Unravelings of tuples of nodes, no?
Mm-hmm.
Okay.
Yeah, you could do that.
Okay.
Then the computation of this distance would be infeasible. I mean,
yes,
you would have still these computational trees, but on the applied on this transformed graph, for example, for the KWL. But you can define everything for these higher order variants.
okay.
The results would be very similar. It would depend on the number of equivalence classes induced by the KWL.
No, I was thinking because when you use this labeling trick, you get different structures, right? And I don't know if these different structures would give you some notion of distance that it's relevant. But,
It would be a very similar distance. So
okay.
in a current work that we have, actually in a preprint that we have, we generalize the idea of MPNNs, including a first step for transforming the graph and then the application of MPNN. So we cover all these cases for the labeling trick and all these architectures.
Okay.
So with the labeling trick, you get trees, but you can also add loops back to the loops.
Yeah, so you have a constant,
Yeah.
basically, yes.
So here is a very nice connection between the covering number bounds and the VC dimension bounds. So this is the general theorem about covering number bounds. And in our work, we defined the forest distance, and for which distance on the space of n-order graphs, we proved that the covering number of the space of n-order graphs with respect to this forest distance can be bounded by and the radius epsilon can be bounded by this number here, which is the number of 1WL equivalence classes divided by the radius plus 1. And this is very interesting because this bounds holds for every epsilon, and if we set epsilon, let's say, to be equal to 0, this gives us asymptotically exactly the VC bounds, showing that the covering number-based bound gives a more fine-grained, accounts for a more fine-grained notion of similarity between graphs. Okay. Yeah. So far we have seen the VC dimension, the Rademacher complexity bounds, the covering number bounds, and in all these cases we do not have any assumption on the space of on the distribution we are actually using. We just say that the graphs ensemble have been sampled in an IID way, and that's good because we do not make further assumption. But there are also works that they also introduce some distribution on how we can generate the graphs. I will not go into details, but I will just mention that there are these works. So you can assume that the graphs have been generated from some graphons with some distribution model, as we saw yesterday, some nice examples, or through some that the graph live on some manifold, and we can sample elements from the manifold and construct the edges based on the distances between the nodes we sampled. So this, I would say more generally that this gives better asymptotically results. For large graphs, they give better results. Okay, so far I have mostly focused on graph level tasks, even though there are some works that account for the node level task. There is a reason I haven't really defined the generalization framework over nodes. And this reason is that almost all these works have these assumptions that the nodes for the node level task have been sampled in an IID way, which is kind of unrealistic in practice. So you can think that in a citation network, of course, the label of a node actually depends on the labels of its neighbors. So assuming that you have sampled its node or its ego graph around the node in an IID fashion is not very realistic. Same issue for the link prediction. You have to do this IID assumption. We have a work that we also account for generalization bounds without the IID assumption. It's a preprint for the node and the edge prediction level. You can check this work. But what is important is that for MPNNs, for link prediction, the things are even worse here, because we don't have only this non-IID assumption, but let's say that we want to predict if there exists a link between these two nodes. So the MPNN itself, in order to apply the MPNN, we need to know if there exists a link between these nodes. So one may say that, okay, you can compute the vectorial representation of these nodes, then combine the nodes and make some prediction about the link. But the question now is, when computing the computational tree of this node, do you actually include the missing link or not? Because this is actually the label we want to predict. And if we include it, then we have implicitly assumed that this link exists, the link that we want to predict. And if we don't, we have assumed that it does not exist. So there is a gap here on how to define the generalization framework. So what does it mean that we are given a graph if we actually want to predict a link on the graph, if we are not even, if we don't even know if this graph is complete. Okay, yeah, finally, I have some main challenges in the generalization theory for graph learning and future direction. So first of all, there are no results for graph transformers, and a very common problem is that when we apply any graph transformer, we don't have these very nice structures here of these computational trees, but instead we have these very regular trees because all nodes are allowed to give information to the other nodes, and the graph structure is hidden somehow with the positional encodings in the node features of the nodes. So that makes it hard to define distances as optimal transport problem between computational trees, or to bound the complexity, looking at as we did in the Rademacher complexity, looking at the complexity of the computational graphs. Of course, there are not results on the foundation models, or very few results on transfer learning. And yeah, it's very important to set a proper framework for what are foundation model, what would be a generalization property for foundations model, because we have seen, Michael showed us that in practice they work. And it would be nice to explain why and what does it mean that they work. Same questions for higher order MPNNs. There are some works that showing this trade-off between expressivity and generalization, but still we haven't really understood when we should stop increasing the expressivity because we start losing the generalization, and if there is some space of graphs that we can measure this. And of course, it is very important to go beyond uniform bounds. So we saw that all these bounds are hold for the supremum of the generalization gap, so accounts for the worst case behavior. That's why they are very loose, they are overly pessimistic, but in practice, what it happens, we use an optimizer. So this optimizer doesn't really found the worst case in the function, but it was a very nice function. So we should somehow incorporate the optimization process into the game. There are some works, but there are mainly from some restricted MPNN or graph convolutional architectures, or following a pack-Bayesian approach that I didn't mention, but it's very similar. But the bounds are non-uniform. And of course, what would also be very nice is to understand the geometry of these graph spaces we defined. So it would be very interesting to see if we can derive tighter bounds. For example, we showed that the covering number can be bounded by the number of 1WL equivalence classes divided by some linear function of the radius. It could be interesting to show if we can go even further, even from some restricted space of graphs. And there is our survey paper here presenting actually all these frameworks that I presented, and a position paper on future directions on graph learning. Okay, yeah, I think that should be all from my part. I'd be happy to take any questions. Yeah.
So I'm wondering, so all of the tools that you present, are the bounds kind of increases with the dimension of the space?
Mm-hmm.
And so this is sort of in contrast of, we know another line of work that does like double descent and over-parameterized model, that they show that using random matrix theory, you can sometimes don't get this monotone increase when you have increasing dimensions. So can you remark a little bit on that?
Mm-hmm. Yeah, I'm not aware of any works with double descent in graph learning, but yeah, that's a very interesting direction, I think.
There
but
was actually one work I think last year in PNAS. I can share it later.
Okay.
And I think they analyzed very restricted setting with very assumptions and trying to discuss the both.
Okay, let's discuss this offline. Yeah.
Okay, great.
Thank you.
Hey, so that was very nice, by the way. So, but does this give you any insight on like how to design the network, how to do something differently in various bounds? Do they teach you something?
I mean, with regards to the covering number bounds, for example, you get actually you can understand it with space of graphs. You can say that MPNNs can actually generalize. So you want the space of graphs to be as much simple as with respect to that distances. So you can, because of this dependence on the covering number. But in terms of the parameters, for example, you can use the Rademacher complexity bounds and see how do they scale with the hidden dimension on the number of layers. And yeah, but I mean, there is this trade-off. I can't really answer this question, so.
It's partially related to what Nadav asked. Let's say that I'm a practitioner and I want to use those bounds for, I don't know, computing the sample complexity or how many samples I need in order to get some good generalization. Did you try to kind of play with the numbers and see what you get?
Not really. There are results relating the sample complexity with the VC dimension, but still the VC dimension, this MNDL, is somehow unknown. How does it scale? So I cannot really answer this question about how many samples would you need from a theoretical perspective to guarantee this nice performance.
I think it's more about getting structure results. Like how does graph structure influence sample complexity, not guiding a practitioner. Okay, like how many actual training samples do I need, in my opinion.
Yeah, I don't think that anyone before training the MPNN would take these bounds and see if it was training or not.
You would like to do something like that, right? But
it would be ideal.
Maybe the bounds are.
It's more like rough guidelines, I would say. When you design MPNNs, that you have some structure to think about.
I think in the WL Meet VC paper we had some result that said if you restrict your class of graphs to ones which can be colored with a finite number of colors, then this replaces the n dependency on n in the upper bound. And so you actually can deal with infinitely large graphs. Let's say regular graphs, then it's really easy. So the bound is also going to be trivial. So
how tight are these bounds? Do we know? Do you know?
No. They are not tight, of course, with the definition of tightness. They are not, but depending on the data set. So in our experiments, we have data sets that the actual generalization gap is very close to the estimated bound. So because we also have to estimate the Lipschitz constant in some sense, yeah. So it really depends on the data set and the loss function.
Another way you can maybe get more like practical insights is if you look at the metrics that you use for like generalization, because they somehow reflect a bit how does your neural network actually see the graph space, like what are graphs that are close from the perspective of the model. And that can help you maybe when you want to do transfer learning or you want to like understand would my model generalize or so, which data points are actually different from the viewpoint of my model. So because it's the same distances you would essentially use that reflect the model's behavior. And that is something that a practitioner could potentially use. Okay, if there are no other questions, then we can switch to speakers.
Okay, hope the mic is on. Okay, so thanks, Antonis, for the introductions and overview for in-distribution generalization. The part that I'm going to tell you, there are two bits. I'm going to talk a bit about some lower bounds that comes from computational learning theory. So this is still in distributions, and then in a later part, I'll talk about out-of-distribution generalization and more focus on the more theoretical sides, and there is a gap between that and what people actually do ad hocly in practice for out-distributions. But okay, so I'll first introduce some ideas about how to get lower bounds for computational learning theory. So what we have seen so far of all these VC dimensions, Rademacher covering numbers, there are some lower bounds, but most of them talks about upper bounds, and what do I mean by upper bounds? They details the conditions under which learning is possible. So how many samples you need, for example. That would be a statistical questions. How many samples you need to learn a certain concept class that you assume your ground truth comes from. And there can be a computational problems, which is a bit harder, as are the efficient algorithms. So if you need like exponentially many samples, of course, there's no polynomial time algorithms to solve this. But if you need like polynomial samples, there may or may not be a polynomial time algorithm that solve your learning problem. Okay, so these are what we are interested in when we deal with upper bounds. What I'm going to talk about is slightly different, and we are looking into lower bounds or impossibility results, asking for conditions under which generalization cannot be guaranteed. And a simple kind of, if you have a bounded VC dimension, let's say a polynomial growth in your VC dimension, then you immediately get efficient learning, another pack learning model. And for a lot of the cases that we saw, it's quite finite. The VC dimension is quite finite. So what we're going to do is that we're going to restrict this pack learning model pack. So for those who are not aware, are not familiar with pack stands for probably approximately correct. It's a very general framework of learning theory that encompasses a lot of most algorithms that you can think of, probably nice in pack. So it can be weird things like Gaussian eliminations. But if I give you data sets, you're probably not going to do Gaussian eliminations on it first. Okay, so there are a lot of algorithms. It leaves a lot of rooms. But we're interested in restrictions, interesting submodels of packs. And in particular, we want to restrict the class of algorithms that we allow that we are allowed to have access to. And while still having access to usual algorithms like gradient descent, gradient-based algorithms that usually run to learn these deep learning tasks. Okay. So I'm going to first define the restriction that I'm putting into the model, and then I'll tell you in a later slide why we care about these particular restrictions, and try to convince you that it's not too strong a restrictions, that we still have interesting algorithms left at our disposal. So the first restriction is that we do not allow the algorithms to have access to samples, independent samples, but rather statistics over sample distribution. And what do I mean by this? It means I'm given a concept or a ground truth that maps, let's say, images to whether this is a cat or a dog in some class of concepts that I assume the ground truth come from calligraphic C. And then I also know the distributions over data sets X, so over the images. What I can do with my algorithm is that I can ask queries, and these are called statistical queries. The input is a function that takes as input a sample. So a sample here consists of both the sample consists of both the input image as well as the label Y. Okay, and the query is going to be bounded, and I also give it the tolerance parameters. What the oracle is going to tell me is, well, a statistics, an expectation over the data distributions of this query, give or take some errors term. Okay. And I'm going to restrict this one step further. I'm going to require that the query Q, so should be Q here. I'm going to require the query Q takes a form of an inner product of a function that depends only on the inputs here, the images, and inner producted with the label Y. And the oracles again returns the expectations over data distributions, and because of my restrictions to the query form, the expectations is now a correlation values over the L2 space with respect to the data distribution, plus or minus some errors. Okay, so that is, and the task is of course to learn the ground truth C from these queries. Okay, so that's the restrictions. I'm going to tell you next slide why we care about these particular restrictions. Are there any questions for? Yes. Right. So you have to, in order to learn the ground truth, you have to gain some information about it. Okay, we don't have samples, but we can gain information by asking about statistics. For example, if let's say your Q, let's say just ignore the first part and just give you Y. The oracle will give you the mean of the labels across the data over data distribution with some error terms. And then you can do Y squared, and then you get another moment. You can compute moment from this. And in particular, for the CSQ model, you can say, for example, your F can be a trained neural network. Okay, you retrain your neural networks, it gives you, this is your F. You can ask the oracle, how does this correlate with the ground truth? And it will give you the correlation between F and C, your trained model and your ground truth, and you can get information from that as well. Yes.
Wanted to make sure. So in the SQ regime, you return something. It's like an expectation
Yes.
for the distribution. But in the CSQ, you just return the inner product, or is there also an expectation?
So the expectation of an inner product is a correlation. So it's the same, but just that when you have an inner product, then the expectation become so if you have a dot product, then the expectation become an inner product in this space.
Oh, you write the L. Okay, got it.
Yes.
Got it. Thank you.
Okay, so now I'm going to tell you why this is useful and informative. Before that, we have to look at what are we aiming for and what exactly do we want. We want a lower bound. We want a definition of hardness of learning. So I give you this task, and I want to be able to tell if this is hard to learn or not. The definition is that a class C of concepts, which is just a class of where you hypothesize your ground truth comes from, is hard to learn under the CSQ model if there are no efficient algorithms. So efficient algorithm only makes polynomially many queries, and also the tolerance is assumed to be of inverse polynomial kind of accuracy. And that's a good reasons why we want to not be too accurate, and I'll tell you a bit about that. And also we want to be doing a good job. Right? We want to learn with a small error epsilon. Okay, so if there's no algorithm that runs in polynomial time with polynomially many bits of precisions that also do well, if there's no such thing, then we say that the class of concept is hard. And the reason why we're interested in this particular restriction is that first, it's a proper restriction of PAC. So we assume you only can query statistics, but if you have samples, you can simulate the statistics. And we assume that the query is bounded, so you just use half being bound in order to have concentrations. So SQ is a subset or equals to the PAC, so you can simulate SQ with PAC. And we assume that the precision is polynomial so that you cannot get away, you cannot be more powerful than PAC by being very precise. Because in the simulations, you have errors that is bounded by Lessing-Hofding. Okay, and it is a proper restrictions because you can learn parity with Gaussian eliminations in PAC, but Gaussian elimination is not an algorithm that is in SQ. Okay, and it's an exponential separations. Similarly, between SQ and CSQ, there is also, in the Boolean case, they are the same. You can simulate one with another. But in the real valued functions case, there is an exponential separations. You can learn, let's say, sparse polynomial, real valued sparse polynomial in SQ in polynomial time, but you need exponentially many queries to learn it in the CSQ model. And more importantly, we still have interesting leftover algorithms that we can use. For example, natural gradient-based algorithms like full batch gradient descent under squared laws can be decomposed into a CSQ query. And this is just the population loss, the gradient of it. With some regularity, you can swap between the gradient and the expectations, and you can do. And if you write it down, you have a term that's independent of the labels. You have access to the data distributions. You can just simulate this part, and this part is a correlation value, so you can query a CSQ oracle. Okay. So that's why we are interested in this submodel. Okay, and before I give you the results, I'll very quickly mention the tools that we use. The main tool that we use in this, and it's quite nice because it has some geometric graph interpretation, and it will be CSQ dimension. And the sort of the intuition is that we are going into the L2 inner product space of all the functions that is in the concept class, and we're going to look for a subfamily of hard functions that are pairwise almost orthogonal in the L2 inner product sense. What I mean by that is that the CSQ dimension is defined as a larger size of a set of functions that they are pairwise almost orthogonal, but you cannot achieve this by making the norm too small. It has to have non-vanishing norm as well. And there is, theorems that can link your CSQ dimension, lower bounds of CSQ dimensions, with a lower bound in a number of queries that you have to make in order to learn whatever concept class that you are trying to learn. And so the main proof directions here is then we're going to go into all of our invariant class of functions like GNNs, shallow GNNs, GCNs, and then find these hard functions that are pairwise almost orthogonal in the data, in the inner product with respect to the data distribution. Right. So before I show the results, any questions on this setup? Okay, so the first result that we show is an exponential lower bound in the number of nodes. The concept class here is shallow GNNs. In the first layer of the GNN, you do simple message passing with some learnable parameter AI and BI here. This is simple message passing with some aggregator and also a sum readout. And you have K1 channels out of it. In the second layer, it's just a one hidden layer ReLU network, and hidden layer has K2 hidden neurons. So a very simple two hidden layer GNNs. The data distribution is Arrowstring with probability half, and you cannot make this too complicated by having a lot of channels. The channels are restricted to have the same order as the number of nodes. And with this setup, we show that any SQ algorithm that learns this concept class up to a constant classification error, and with some tolerance tau, will require at least exponentially many number of queries to learn this concept class of shallow GNNs. Okay, and so this is lower bounds in the total number of nodes of the graphs. You also have lower bounds, exponential lower bounds in the feature dimensions, and the concept class is just GCN. So GCN just do some neighbor features and apply the linear map to each of the aggregated features, pass through a non-linear function sigma and another linear map at the end with a sum aggregator. And the input distributions that we are considering is Gaussian. So the data matrix are ID Gaussians, and the graph distributions can be quite general, doesn't have to be Arrowstring, it can be anything, as long as the zero graph doesn't have positive mass. With this, we have lower exponential lower bound. In learning GCN, that if you require, even if you have constant graph size, if you want to learn this function, this concept class, GCN concept class, up to error epsilon, then you must make exponentially many queries or one queries with extreme precisions, which we not allow in our definitions of learning learning under CSQ. Okay, and the tools that we use are like a graph invariance version of Hermit polynomials. Hermit polynomials give you an L2 like orthogonal basis of L2 like square integrable functions over the Gaussians, and this is a graph version of it. Okay, so that concludes the part where I talk about lower bounds from CSQ models. Any question on that before we move on to the next part? Yes.
Can you assumptions about the activation function?
With Lipschitz. Yes.
Does this cover the
where there is no graph, like A becomes identity, and does that reduce to some of the known bounds?
Yes, so the graph distribution cannot be too degenerate. Like the NC graph cannot have, let's say, constant mass. So yeah, no, we don't allow that.
So how does this result compare to the result on the IID sample case? Like, is it similar rates?
You mean for like?
Let's say a MLP, and then I only have X, like no graph.
So I'm not exactly sure what you mean by the IID
So
case.
I guess I'm curious on, I guess before this, there must be some results using CSQ to analyze just the standard case where there's no graph. I only have
Okay, just an MLP.
Yeah, and then I maybe just use a one-layer MLP. And so, or does your result already encompass that result?
Yes, so there are existing results for just learning two-layer neural networks. Again, an exponential lower bounds. The hope that we had going into this is that the the invariance, because GGN is invariant for mutations, we hope that that kind of savings will help us beat the exponential lower bound. But it turns out that it still holds. But albeit this is a weaker lower bound than what is known in the non-invariant case.
So is there any gain or no?
There is gain, but it's not enough to beat the exponential
The
lower
rates is
bound.
still the same, but then
Yes.
the exponent might be different.
Yes.
Thank you.
Okay, if not, then we can go on and talk about out-of-distribution generalization. And I'm going to be very liberal with what I call out-of-distribution generalization, because some people have very specific ideas of what out-of-distribution generalization means. But for me, and in this particular talk, if during your training there is a part of the test set that you are not going to see, then I would count it as out-of-distribution generalization, and it encompasses many things. For example, size generalizations or transfer learning, or things that like algorithmic alignment, which we'll touch each a bit later on. Examples, of course, size generalization. If you are only restricted to bounded number of nodes in your training, and then you hope that in testing you can have a largest graph, and it still do well, then it's out-of-distribution generalization kind of guarantees that you're looking at. Or degree sequence. If you've never seen this kind of degree distributions in your training, can you hope to do well in testing? Okay, an example and like the motivation why we would think this is possible is in practice we never get arbitrarily large training instances. We only get smaller training instances. But in testing, we may encounter graphs that may come from the same data generation process, but it's larger, and we've definitely never seen this before in training. So I came from size generalization, so I gave a size generalization examples. There are many other examples. And to have any hope of doing any of this, okay, you have to make a coherence assumption. You have to know something right. Okay, if you don't know anything about data generations, about architectures, then there's no hope for OD. And I'm going to organize the talk based on what you know to be right. Okay, so there are some assumptions on data or architectures or optimization algorithms, and you hope that your other assumptions are not too wrong. Okay, right. So the first thing that you can get right is the assumption on the data model, data generating process, and the guarantees you get if you get this assumption right is usually from approximation theory, things like graph limits, things like random graph model that we heard from Samuel yesterday. Or you can get the architecture's optimization process right, then you have some guarantees over there as well. Or there are more ad hoc cases where there's some environment that governs your distribution shift, or there's some known transfer learning kind of actions going on behind the scene. If you know this ad hoc, you can have ad hoc methods as well. Okay, so I'm going to go into the first part where you have some guarantee based on approximation theory, and the kind of like general observation of why this is possible at all is because things like GCN's parameterization does not depend on the size of the graph. So this is a definition of a GCN. Probably everyone would have seen this by now, but it's defined recursively. In the input, you just have node features. In each layer, you applied a linear operator on the previous node representation of the previous layer, and then you do some nonlinear transformation. Okay, and for example, in GCN, the linear operator is a polynomial of your graph shape operator, and the learnable parameter here are the coefficients of this polynomial. So obviously, this is a pointwise multiplication, so your parameters does not care about the size of your graph at all, which comes up in the size of the matrix here. So you can just train on small graphs, for example, and then you plug the same parameters on testing time, and it's completely well-defined. Whether it works or not is a different story, but it's well-defined. We can reason about it. And you can even put things to the limit, and but you have to make all the well-defined assumptions. You can replace the graph shape operators, Laplacian or adjacency, with that that of the limit operator. Examples include kernels and continuous GCNs that Samuel talked about, graph forms that Luana talked about on Monday, and sparse graph limits, which if you were here for my lightning talk, I talked about for like 2 minutes. So I'll explain a bit more carefully later.
Yeah, so one thing that I'm finding a bit confusing is that it seems that the assumption is on the MPNN or whatever you're using, when the assumption is about the causality of the data, right? Like if I do an intervention on size, then what would I see as generate a graph? Under those assumptions, then this works for some assumptions, but not all assumptions.
Yes.
Right?
Yes, so this is an assumption. So the GCN here is an example. Most of this, I believe, to work more generally, as long as...
No, but it has nothing to do with fact being a GCN. It has to do with the distribution shift caused by some intervention on sizes.
Yes.
So under some assumptions on that, for instance, if it's a graph form, right? For a graph form, we can say, oh, here's the size, and you can create bigger size with the same, larger graphs with the same graph form, right?
Yes.
And then all of this works because under that assumption, all these things converge, etc. But if you remove that assumption, if you have a different causal model for the graph,
yes,
none of this is going to work.
Exactly, yes. So as I mentioned, if you want OOD, you have to get something right. And this is the part where I talk about you get the data generation assumption right. So I'm assuming throughout this first part that the data generation process is correct. In later parts, I'll talk about what happens when you don't have that assumption.
But do you know what the data generation process is supposed to be for this to be correct? Like what their assumptions are of the data generation process?
Right, so for example, it comes from, you can sample it from a graph
for sure, yeah.
Or a continuous GCN, Samuel talked about yesterday, or if it's some kind of resolution, super resolution.
But I just don't understand. The continuous GCN is the function you're applying on the data. It has nothing to do with the data itself. I don't understand that, sorry.
So continuous GCN has a random graph model at the limit that you can, that turns out your finite graphs.
Okay.
Maybe you can discuss offline. Yes. But yes, in this part of the talk, we assume that you have the right data generation process, at the limit somehow.
It's an important point. I'm also confused actually.
Oh, okay.
Like you're working about distributions, which are about the data, but your focus is on the computational model that you use for the learning. So I was expecting assumptions on the input and not on the computation GCN or...
No, so this is not an assumption on this is just to demonstrate that you can reuse parameters, or you can even hope to have, you can just plug the train parameters and use it for the testing on larger set. Doesn't have to be, there's no assumption on the architecture at this stage.
So I think its assumption here is still that there is some kind of graph limit model, and that's the data assumption. And the model is just to illustrate how you would apply the model on graphs of different sizes, is that right?
Yes, precisely.
But under different graph limit, under different models, there are different graph limits, and this is not universal, right? It's not for all possible graph limits, is it?
Right.
For all possible graph generation processes. I think that's not
That's still an assumption on the data, which graph limits notion.
Right, there are some graph generation process for which you have limits, for which this works.
Yes.
But not all generation processes that have graph limits, this works, correct?
Sure,
Okay.
yes.
I think I understand now.
Yes. Okay, so this part is a recap of Samuel's talk on his bounds yesterday, so I'm going to go through it a bit quickly. If you have, for continuous GCN, you can replace the shift operator of your normal graph with a limit object that is fully prescribed by a continuous kernel and also specified by a random graph model at the limit. And there's also some coherence between the continuous and discrete input spaces, and there's assumption on smoothness on that part. So what I'm find interesting is the shape of the bounds. Okay, so the particular constants and things are not too important. I just want to highlight some parts of the bound. And here you can pick any error failure rate row if you have enough nodes, so your graph is large enough. And nice things about Samuel's kind of bound is that you can play around with the density. You can go up to hypergraph level of sparsity of n log n kind of number of edges. And then with high probability, you get a bound on the MSE of between your finite object and your infinite object, your GCN output and your continuous GCN output, where the Z and the F are coupled with the data generation process. Okay, so the bound here, let's first talk about the rates. So there are two terms that depends on n. When you have dense graph, this alpha term is going to be constant, so the rate is the same for both terms. You have n to the minus half rate, which is standard. But if you have a sparser graph log and average degree, let's say, then the second term dominates, and you have a slightly lower rate. Okay, so things that appears in the bound include this sort of log 1 over rho, which is standard in a lot of the bounds that you see in the distribution part as well, and also this dependence on dx, which is a Minkowski dimension that captures the covering number of the space. In the space here, the structure of the space comes from the limit model of the continuous GCN, where you have the support X that is equipped with the metric D that make the space compact. Right. So that's the first bound that we show, that we were seeing in much more details yesterday. Now I'm going to talk a bit about graph fonts, and so we've probably all heard of graph fonts from Luana's talk and many other talks. This is a picture from Yufei's textbook, where you have a very heterogeneous community, two community graphs, and then if the more you draw nodes or members from the communities, it converges to these functions on the unit square that is piecewise constant with 4 pieces. Graph fonts are bounded symmetric measurable functions. You have an informal interpretation of an infinite graph with continuum number of vertices, and the edges are just based on the function values. And you can have a more formal definition in terms of a graph, finite graph sampler. You first sample the vertices, then you sample the edges with a bias coin flip, and the bias is set by the function value. Okay, so this is should be quite familiar. I'm going through it quite fast. This is Luana's bound that she also showed on Monday. And again, the interesting things are like to go through what's happening in the bound. And I like this bound not because it shows some different perspective in terms of signal processing. Okay, so this is very different bound from what we've been seeing from in generalization with covering numbers and random marker, etc. Okay, so there are 3 terms. The first 2 terms are actually very fast. First 2 terms have rate order n to the minus 1, which is extremely fast. You don't really expect this, but then you pay it off with a non-vanishing term at the end. So this last term does not go down to 0 with n, and I think this is I call this a non-transferable energy, and all of these things that happens here, all of these parameters are spectral in the spectral domains. Okay, so what happens is that you first choose a C. The C will, and then you have eigenvalues in the gap from minus C to C. And you don't expect to be able to recover information for eigenvalues are in this band because there's just too many of them, and then they fluctuate quite well. They're possible to in signal processing. You don't really expect to be able to get to reconstruct things that are very high frequency. So there are two parts. The first part is the eigenvalues in minus C to C, and then the second part is outside of it. Then inside of it, you have some Lifshitz constant. Outside of it, you have some Lifshitz constants. Then you have all the spectral kind of invariants or spectral expressions based on that interval. Okay, so depending on how you choose the intervals, the outside part you can control very fast, very quickly with order n to minus 1, and the inside part you just assume is not transferable. And of course, you can play around with this C. You can have C to be a decreasing sequence in n, and then you get some actually converging to 0 rates. But I mean, this perspective is interesting and a bit more interpretable, I'd say. Okay, so that's the graphon part. Now I'm going to spend a bit of time talking about sparse graph, but I'll probably speed up due to time. And the first thing that I'm going to try to convince you is that sparse graph is non-trivial. And the reason for that is that eigengap is not continuous in the local convergence settings, which we've seen. I'm not going to define, again, local convergence. We've heard about it yesterday. But spectral properties start to break down when your graph have very sparse, when your graph is very sparse. Okay, and here I had a quick proof, but I'm probably not going to much details into it. Okay, to construct a sequence of sparse graph whose eigengap is discontinuous, you start with 2 disjunct copies of random d-regular graphs. So you can construct random d-regular graphs by configuration model or Chung-Lu model, depending on your reference. But you can construct finite d-regular graphs, and you have a growing sequence of them. And you have 2 disjunct copies in each part. Okay, so this GI sequence of growing random d-regular graphs, 2 disjunct copies, is known to converge to an infinite d-regular tree. So the difference between a graph and a tree is that a tree doesn't have any cycles. And you can it's a very quick kind of counting arguments to see that the expected number of cycles of any size, constant size, is constant in a typical random d-regular graphs. So in the limit, it's going to look like a tree. You're not going to loop around. And well, the eigengap of each element of GI is 0 because it's a disconnected graph. We have disjoint copies. But the eigengap of an infinite d-regular tree is something that is bounded away from 0, assuming that d is at least 3. So that's a discontinuity. But even with this handicaps, people are still able to prove, let's say, convergence result for sampling-based GNNs that we heard about yesterday. Okay, I'm going to very quickly mention more unifying kind of approach to sparse graph limits in operator sense. So if you were here yesterday, I apologize, but I'll repeat this for like 30 seconds. So this is a picture, a very nice picture from Backhaus and Jerry's paper. Dense graph limit graphons is here. Your local convergence graphings is over here. And there are many other things like LP graphons, Markov graphs, and other stuffs. Okay? But the unifying kind of objects, mathematical objects, is an operator, called P operator. And I would, my opinion is that P operator plays well with deep learning, and you can do interesting things of it. Here is a quick sort of like brief through the definitions of P operators. You start with a graph. You have an operator from the graph, an adjacency matrix, let's say, and then you apply it to some arbitrary node feature sequence. Right? You get another one. And if you pair the columns here together, you get point masses in R2. Okay, so any graph, you start with any graph of arbitrary size, can be 100, can be 1,000. You end up with a distributions on R2, And you can also not stop at just one node features, but you can do k node features, and then you end up with distributions in R to the 2k. And if all of this set of distributions converge at the same time together, then we say that the operator or the graph converges. Right? And the important thing is that with this metric, the space of P operators with this metric is compact. And with compact comes finiteness and all these covering number bounds. Okay, so I'm going to quickly mention our result. For this, we have a heavy hammer tool that with transferability bounds for this. But let me first tell you about discretizing. So I start with a limit P operator, and I'm going to tell you how to discretize it. And the intuitive idea is that you're going to average connections between, so if you start with a continuum 0, 1, and you want to discretize it into a finite graph of, like, let's say, size 4, right? Then you're going to split the interval into 4 equal parts, and you're just going to average out the interaction, the connections between each of these parts. Not going into more details, but under super resolution assumption, which is very strong, but we verified, satisfied by things like path graph, grid graphs, hypercubes, like you can have repeating motifs like polymers, and even for dense graph like graphons. Under super resolution assumptions, you have a convergence rate of typical convergence rate. So this is a very strong assumption. I'll be the first to tell you this is a very strong assumption. I would love to be able to relax. Okay. Okay, I'm going to quickly talk about the second part when you don't have data generation kind of guarantees, but now you are correct in something else, and this part is about model architecture. Now, this part starts nicely with a lower bound. Okay, when extrapolation cannot be guaranteed. This comes from a paper by Yehudai who worked with Maron, with Hagai. And here I'm going to define a D pattern. So a D pattern encodes D-1 pattern and of itself and neighbors, and at 0 it's just a node features. So the 0 pattern of this particular node is just a node feature. Then the 1 pattern is the 0 pattern of itself, and then the 0 pattern of its neighbor. Right? And the 2 patterns is the 1 pattern of itself, and then the 1 pattern of its neighbors. Okay, so and this should be very familiar with what we are doing with computational trees and all of that. But this is how it was defined in Yehudai's paper. Okay. The setup is that you have P1 and P2 distributions over graph. This is your training data sets. P1 is your training, P2 is your testing. And then you have, with this comes induced distributions or a multi-set of D patterns. Okay, so if you assume that any graph in your testing P2 contains a node with a D pattern that you have not seen before in P1, so this means in P2 but not in P1. So if for any graph in your testing, there is a node that you have not seen the configuration or the patterns before in your training set, then if I give you any GNN that solve the training data sets with depth D, then there is a slightly deeper GNN with D plus 4 depth that's also solve the training perfectly, but the testing becomes arbitrary. You can make arbitrary errors. So this is the lower bounds. And in fact, this lower bounds hold a bit more continuously in a sense that the D patterns here are actually computation trees, right, when you run MPNNs or GCN or local updates. Okay, so you can do this more continuously by defining a metric over D patterns, and it will correspond to the metric over computation trees of depth D. And you also have the recursive definitions, which fits both the D patterns and the computation trees. And with this comes the tree mover distance introduced by Jingyao Zhang and Stephanie Gelkas in 2022, where, well, first you look at the root difference. D pattern is the D-1 pattern of itself and the neighbors. So this is the difference at the root itself. And then with the neighbors, you're going to compute the optimal transport distance, because you don't really know which subtree to map to which. So you're going to take the minimum one that usually gives you a norm. And in order to do OT over this space, you have to have a metric space over trees. And again, you already have a metric space over tree, which is recursively defined. And so this is a metric over trees. You can get a metric over graphs over it by just having each node as all computation trees from two sides of a graph, and then you do OT first. Okay. So this basically gives you a computation, like a metric over computation graphs, which is your architectures that you're actually working with. And the kind of like similarities or the correctness assumption here for all the distributions is that you get the correct architecture. Okay, so I'm going to give you very quickly the bounds. So this is a continuity bound or transferability bound, depending on the community. But if you have, this is a GIN. I'm not going to define GIN again, but this is a GIN. If you have a layer GIN, then you have a Lifshitz bound with this Lifshitz constant and the corresponding TMD metric. If you have a different architecture, like a GCN, the definition of the TMD will change slightly. If you have an even different architecture, it will change slightly. So this kind of metric depends on your architecture. And there are people have successfully applied this to do things like dataset subsampling by chains and LNs. Okay. Now I'm going to very briefly mention what you get in terms of OOD, in terms of algorithmic alignment. I'm not going to go into any details into this because we're going to get wonderful talks from Yusu who will talk about this a bit later. Algorithmic alignment is the paradigm where you try to design neural network architectures that resembles classic paradigms in algorithms such as dynamic programming. And the intuition is that if your graph neural network computation kind of like loop looks like, let's say, Bellman for algorithms for shortest path, then you can learn, like the learning task is simpler. You only need to learn this function that is just a minimum and then an addition. Right? So that's the intuition. And so far, it's very intuitive, but it's hard to formalize. Not many people have proven formal bounds on this. And the recent paper by Nerem Chen and Dasgupta and Wang gave some very nice theoretical guarantees. If there's a special training data set and a special training loss, that if you can learn that with up to error epsilon, then it implements Bellman for up to error of the same order. And hopefully we can hear a bit more from Yusu at a later talk. Okay, so now I'm ready to conclude. For all the distributions, you must get something right. Either you get data assumptions right, and there can be many different data assumptions. If you get like things that are right in terms of limits, then you can get approximation bounds. Or if you get architectures, optimization process right, get things like tree mover distance, guarantees based on tree mover distance, or guarantee based on algorithmic alignment. And of course, there are, in the real world, there are more ad hoc things that you know about your distribution shift, your transfer learning settings. You can do all of this in a more ad hoc way, and it usually works better. But for more theoretical guarantees, I chose to focus on the first two. But yes, that's the end of the presentation. Is there any questions for this?
I have a question about the non-transferable energy in the so is that the necessary? Because I think that I don't know if it's other works by Luana or Ron that don't have that term that doesn't go to zero.
Yes. So my answer is that it's not necessary. Let me quickly go to it. Okay. So I would say it's not necessary because even from this bound, even if you don't need any new techniques, if you start from this bound holds for any C, any of the bandwidth that you choose. So you can let C be a decreasing sequence of n. And then all these other parameters change. The number of eigenvalues, of course, will change. Will scale in some orders. If you can put in like a Sobolev space, and then you can quantify exactly what the eigenvalue counts would be. So if you let C be a decreasing sequence of n, you can get something. You can get something that decreases to 0. But I agree that this bound is also interesting because of its interpretability. No, then thanks everyone for the things.
I have a quick question. Like one interesting aspect could be that where the graph structure or the sampling of the graphone and the sampling of the size of the graphone, right, which are some to be independent. If they have some kind of dependency, then you see it would see the process, but in the causal procedure, it look very different. So you would end up with very different, possibly very different results.
I completely agree. I mean, these are more, to me, the interesting things about this approximation bounds is that you have discontinuity towards the limit. If you want to, put things on top of it, like you have a cupboard, like size kind of choice, it's definitely going to be got a different bound, and I'm not sure how exactly it will look like, but that will be task. Like it depends on what. Yeah, I don't really have a very insightful answer to that, but yes, I think the point of having a graph limit model, for example, is this discontinuity things that you.
Yeah, but like what I'm saying, like trying to say is like it's interesting that there is a completely new way of looking at this, where you say, well, the graphs and the sizes are there's some dependency in the sampling of the graph and the size, and that is a different avenue, right, to pursue. Because usually, like natural graphs, the sampling and the sizes are correlated.
Yes, like in social networks, you add users in conditioned on existing things. So yes, that condition is only going to be very complete. I mean, you can probably write down pages and pages of algebra to solve it, but and then I'm not sure if there's I mean there must be simplifying assumption, like can be a martingale sort of process, and then you can get some bounds over it, but have not really go through the algebra to say anything concrete myself. Yes.
So for this lower bounds, I wonder whether there is some sort of natural ways to break those lower bounds, because those are kind of in some sense the worst case, right? But we also know that in practice, for example, in the training procedure, you can have some implicit regularization. I wonder whether there's some natural case of this regularization that can break those lower bounds, so that even though that in worst case they will happen if you don't have anything else, but then maybe through the typical training,
yes,
you don't get to those. Yeah.
Yes, I mean that's an excellent question. The lower bound I showed in terms of computational learning theory is when you have a restrictions of your algorithms only lie in this CSQ model. You cannot let's say do Gaussian elimination because that's not part of the model. And what I showed is that full batch gradient descent on squared loss is CSQ, but I didn't say that, let's say, stochastic gradient descent is in CSQ. In fact, stochastic gradient descent is not in CSQ. And it can, there are results by Abe Emmanuel in EPFL and Sandons says that you can actually simulate a lot of things in PAC with stochastic gradient descents. So that doesn't solve, we don't really solve the lower bound problem of that gradient descents cannot learn it. Stochastic gradient descent may still just learn it as well. Regularizers, I do not think will, unless you have like the usual L1, L2 I think it's still like the corresponding ERM associated with that is still CSQ for full batch gradient descent. So that may or may not help, but the actual crux of the algorithm itself being stochastic gradient descent may help us overcome that lower bound.
Okay, if there's no further question, then we'll have a coffee break until 11.